Hi, everybody. Good morning. We've reached the last part of the last unit. So we are still in infinite sequences and series. We're looking at unit 6 power series. Power series are a very specific kind of series. It's an infinite sum of series of the form, a sub n, x to the n minus c, x minus c to the n. I said that backwards. And what I have below is that expanded form. So the more common way to think of it would just be like, zero. No, goodness. Can you tell it's a Friday? 1 plus x squared plus x cubed plus x to the fourth dot dot dot. That 1 would really be x to the 0. Remember, anything to the 0 power is 1. And then this minus c, what that is it's a shift. Remember when you were graphing parabolas, if you had y equals x minus 2 squared, it would take that parabola and shift it to the right too. This is that same idea. It's a shift in either direction. So to make use of power series, we need to determine for what values they converge. Each power series converges absolutely on an interval that is symmetric around C. So when they converge, when does that power series actually match up with the polynomial? When do those two things match? So your radius of convergence is where they absolutely meet up and match up. So you've got three possibilities with these. F of x converges for only x equals c, only at one point. F of x converges for all x, that they match exactly. Or there's a number r greater than 0 such that f of x converges absolutely if x minus c is less than r and diverges if x minus c is greater than r. It may or may not converge at the endpoints. So we have a radius of convergence. So what am I talking about here? I know this is a bit of what's going on. So say I have a polynomial, whatever it looks like, and I'm going to estimate it with a power series. My choice is if it converges for only one x equals c, I'm going to just call this my c. It means that it would pass through only one point where they match. That's option 1. Option 2, it converges for all x. That would be if it overlapped exactly. Option 2 would be a perfect match. And then here's option 3. There's a number r greater than 0 such that f of x converges absolutely. So if it converges, remember that purple is the original. If it converges, say, from here to here, here's my c in the middle, and r is that distance to the left and that distance to the right. I know this is a little bit messy, that it matches up perfectly, but beyond that, it doesn't match up. And then you have endpoints that you have to worry about as well. So my Algebra 1 class, believe it or not, is graphing inequalities on a line. It's the same idea. You could have an open circle or a closed circle, depending on what's going on. So I know this seems like a lot, but we can do this. We're going to use a lot of the ratio test today. Example 1. F of x equals the series from 0 to infinity of x to the n over 2 to the n. For what values does f of x converge? So the first thing that you have to do is 1, use the ratio test. So remember, for your ratio test, it is the limit as n approaches infinity. We have x to the n plus 1 over 2 to the n plus 1 over x to the n, 2 to the n. And we want the absolute value of this. So instead of dividing by a fraction, we multiply by the reciprocal. X to the n plus 1 over 2 to the n plus 1 times 2 to the n over x to the n. And then we're going to simplify. So I know we did a bit of this in the last unit. X to the n is gone. You're going to have an x left in the numerator. Same thing here. You're going to have a 2 left in the denominator. It's going to cancel with this. How do I want to do this? If I had x to the 4th over x to the 3rd, you know that you've got 4 x's in the top, 3 x's in the bottom, you'd simplify and be left with an x. That's really what's happening over here. This is practice in exponent rules. And I'm left with the absolute value, the limit as n approaches infinity of the absolute value of x over 2. So there's no place left to substitute infinity. All the n's have canceled out, so we don't have to worry about that. But I do have the absolute value of x over 2. You can actually pull out a 1/2. So this would be 1/2 the absolute value of x. Now we want to know where this converges. So it's going to converge when that ratio is less than 1. So by the ratio test, my function converges. This would be on that chart if rho is less than 1. So in this case, or that ratio is less than 1, 1/2 absolute value of x is less than 1. And now you have to solve it. So multiply both sides by 2. The absolute value of x is less than 2. And now we have to apply inequality rules. By the way, the radius of convergence, because sometimes they'll ask that as well, is this one 2. That's your radius of convergence, is actually 2 here. Okay. Give me a quick second. Converges. All right, we're good. So if it converges when that radius is less than 2, it will diverge when that radius is greater than 2. But the question is what happens at 2 at the endpoints. We'll get to that in a second. So the second thing is to apply inequality rules. True story, this is absolutely what we're doing in Algebra 1 right now. So remember, absolute value of x is less than 2. You're really writing these twice if they're a little bit more complicated. X is less than 2, and then the other version is x is greater than -2. You have to flip the inequality and introduce the negative sign. So if you're thinking of combining these, -2 is less than x, which is less than 2. This is interval of convergence. You would also have, you could say your radius of convergence, and I know we mentioned that above, radius of convergence is 2. So sometimes they want the interval of convergence, sometimes they want the radius of convergence. You just have to know which one they're talking about. And then the last step is to test the endpoints. Test your endpoints. So your endpoints, because this one is centered at 0, it didn't shift anywhere. You have to test your endpoints, which are -2 and 2. You place them into the original series. SERIES, there we go. So what am I doing? Well, need more space. So those are x values, your -2 and your 2. So we are going to look at this series from n equals 0 to infinity. -2 for x to the n over 2 to the n. And then your other endpoint is +2. So n equals 0 to infinity of 2 to the n over 2 to the n. And what you have to do is figure out if these converge or diverge. So you're going back to the stuff that we did at the beginning of the unit. Now let's just look at this one. -2 to the n over 2 to the n. Remember, you can kind of break things apart here. So we've got a negative, let me do this. This would be a series from n equals 0 to infinity, a -1 to the n over 2 to the n over 2 to the n. Your 2 to the n's over 2 to the n's cancel. So this becomes n equals 0 to infinity of -1 to the n. Well, does that converge or diverge? It's going to diverge. it goes positive 1, negative 1, positive 1, negative 1, positive 1, negative 1. But you can also think of this as a geometric series. So because that ratio is equal to 1, it's not less than 1, you can say it diverges by a geometric series. So therefore, we can't include the negative 2. So let's come over here and include a positive 2. So if I look at this, I've got n equals 0 to infinity. This would be 2 over 2, both to the n. This becomes 1 to the n. Does this converge or does this diverge? Well, just like the other one, this diverges because it's a geometric series and that ratio is 1 or greater. So your radius equals 2. Your interval of convergence is negative 2, which is less than x, which is less than 2. Now, how would this change if something converged? If something converged, you would include those endpoints. And how do we show that we include the endpoints? You underline the inequality. Lots. I know. This is so much. All right, let's keep cruising along here. Determine the convergence of the following series. Negative 1 to the n over n, x minus 5 to the n. So first of all, this one is centered at 5. That's what that x minus 5 is. So let's jump right in with our ratio test. So this would be the limit as n approaches infinity. Remember, all of your n's become an n plus 1. So negative 1 to the n plus 1 over n plus 1, x minus 5 to the n plus 1, all over negative 1 to the n over n, and x minus 5 to the n. Okay, so we can multiply by the reciprocal. I've got the limit as n approaches infinity. Negative 1 to the n plus 1 over n plus 1, x minus 5 to the n plus 1. This is a negative 1 to the n. This is an x minus 5 to the n. And this is my n in the numerator. A lot going on there. Let's just focus on one thing at a time here. What's going to cancel out? Well, I have one more x plus 5 in the numerator than I do in the denominator. So this will just be x minus 5. Same thing with my negative 1s. I've got one more in the numerator than I do in the denominator. So this becomes the limit as n approaches infinity of absolute value, negative 1, x minus 5, n over n plus 1. Okay. I'm going to do a little rearranging here. Move this over here. Put my absolute value back where I found it. I'm going to keep moving this piece. All right, there we go. Now we have to go through and solve this. Don't forget that we are finding the limit as n approaches infinity. So you have x's in there, you have a 1 and a 5, but when you're looking at the limit as n approaches infinity, you just want to focus on the pieces that have the n. So if I find the limit of just the pieces that have the n, okay, n goes to infinity, I have infinity over infinity, L'Hopital, or a couple other ways that we've dealt with that, that will all become a 1. So when you take the limit, you're going to have a negative 1 times x minus 5, except I just goofed. And then this is a 1. What do these absolute value bars tell us? Don't worry about the sign change. So I don't need this negative 1. Okay. Okay, awesome. Now, where does this converge? Well, it converges when that ratio is less than 1. So I'm going to say that the absolute value of x minus 5 is less than 1. Set up your inequality. And then you can write this as two problems. This is the Algebra 1 teacher and me right now. We're saying x minus 5 is less than 1 and x minus 5 is greater than a negative 1. You can actually put all this together as an and problem. You can say -1 is less than x minus 5 is less than 1. You can put those two things together. Add 5 to all three sides, you'll get 4 is less than x, which is less than 6. So there's your interval. There's your radius equals 1. And we know our radius equals 1 from here because we isolated the absolute value. Now you got to check the endpoints. And your endpoints are 4 and 6. So you go back to that original series, n equals 1 to infinity, -1 to the n over n. You put 4 in for the x, and then you put 6 in for the x. So now you have these two problems and you have to figure out, okay, do they converge? Do they diverge? So let's do this 6 first, because I think that one's a little bit easier. This is x equals 6. So this will be 6 minus 5 is 1. So everything out here is just 1. 1 to the n is still 1. So this is n equals 1 to infinity, -1 to the n over n. What kind of series is this? Well, this is an alternating series, that -1 to the n. The 1 over n is continuous, continually decreasing, and does tend towards 0. So this one converges by alternating series. It would be conditional convergence, if you were curious. And then the other one, the one where x equals 4, this one's a little bit different. 4 minus 5 is a -1. So now I have n equals 1 to infinity, -1 to the n, -1 to the n over n. Well, -1 to the n times -1 to the n, you can actually multiply the insides. That becomes a +1 to the n. And +1 to the n is just 1. So this is the series of n equals 1 to infinity of 1 over n. Does this converge or diverge? This one diverges. This is a harmonic series. The easier one is the p-test. Because your exponent down here is a 1, it diverges by the p-test. So what does your final answer look like? Your answer looks like, because it diverges at the 4 and converges at the 6, 4 is less than x, which is less than or equal to 6. If you're using inequality notation, if you use interval notation, it's 4 in parentheses, 6 in a bracket. Oh my goodness, that's a lot going on there. All right, I'm gonna take a quick break and I'll be back to explain the others. All right, so change of location. Theorem 2, finding the radius of convergence. Let F be that series, that power series that's centered at C, and assume the following limit exists. So that's what we were doing up above with that ratio test. And F of X has a radius of convergence R equals R to the -1, where we said R equal to infinity if R and R equals 0 and R equals infinity. I know that seems like a lot. Go with the radius that we talked about earlier. For example 3, show that the following series converges for all x. So just like up above, you're going to start out with your ratio test. So we'll say the limit as n approaches infinity of n equals 0 to infinity. Don't put the series there. Wake up here. X to the n plus 1 over n plus 1 factorial over x to the n factorial. There we go. And instead of dividing by the fraction, we multiply by the reciprocal. X to the n plus 1 over n plus 1 factorial times n factorial over x to the n. And then we need to simplify this. So my x's, I will have 1x in the numerator over 1. And now I'm looking at n factorial over n plus 1 factorial. I do this for real when I'm thinking about them. I'm thinking, all right, 3 factorial over 4 factorial is 3 times 2 times 1, which is over 4 times 3 times 2 times 1. So those cancel out, so I'm left with a 4. So there's an n plus 1 in the denominator. Now, remember, this is still a limit problem, so we're looking for the limit as n approaches infinity. So this infinity goes in place of this n. So now I have x, which I know we're used to substituting there, but you don't. X stays as x. So you have x over infinity. So this becomes, believe it or not, 0. Remember that a number over infinity is really 0. So this is equal to 0. So now, you know what? I wrote this nicer in my old notes. Let me show you a better mathematical way to say this. Back here at this step, you can actually split it into 2 limits. The limit as n approaches infinity of x, and the limit as n approaches infinity of 1 over n plus 1. This piece on the right becomes 0. So this is the limit as n approaches infinity of x times 0. But there's no place to put that infinity because it's just an x. So this is x times 0, which is 0. Another way to look at it. So you have to set that equal to 0, or excuse me, less than 1. So 0 is less than 1. Now in the previous problems, we solved for x, but there's no x left. It's gone, it's just a 0. And because this is always true, your series converges for all x. So if that x cancels out of the limit problem, then it does converge everywhere. I know that feels a little weird. All right, last one here. Example 4, find the radius and interval of convergence for the following series. So this is going to put it all together for us. All right, so first things first, use your ratio test. 0 to infinity. I'm going to rewrite the problem. What can you tell about this? It's a power series because here's your power. It's centered at 3 because of that x minus 3. So this is the limit as n approaches infinity of n plus 1 factorial x minus 3 to the n plus 1 over n factorial x minus 3 to the n. So let's simplify this. We'll have n plus 1, and then you'll have an x minus 3. N plus 1, just double checking my work, those factorials cancel out, and an x minus 3 to the first. Okay. If we put infinity in place of the n, or let's break this apart like I did in the last one. The limit as n approaches infinity of n plus 1 times the limit as n approaches infinity of x minus 3. So infinity, and for n, well, this is left with infinity. In the second piece, there is no place to substitute that infinity because there are no n's. So this is x minus 3. I just got infinity, right? Just got infinity. So infinity times x, this is infinity. This diverges. All right, so diverges. So it does not converge anywhere. It's centered at 3, but it doesn't converge anywhere. If I scroll back up to the top of our notes and we look at those 3 possibilities for radius of convergence, we have the version where it converges for x equals c for only at one point, where it converges for all x, or where we have that specific radius. So if I look at the problem that we just did, we got that it diverges everywhere but that specific point. So your radius of convergence is 0, and it only converges at x equals 3 because that's where it's centered. The whole thing is centered at 3, so that is the only location of convergence. This is going to take a little bit of practice. That's okay. That's okay. do the best you can. Ratio test, you're looking for your ratio test. Set it less than 1, solve for x, and then that's your radius of convergence. So I think those are pretty okay. When you get into the zeros and the infinities, those are your unique situations. So good luck and make sure you reach out with questions.